Hello, everybody, and welcome to everybody's favorite section of AP Chemistry, which is all about intermolecular forces. So if you've taken Chem 2 already, you are quite familiar with these intermolecular forces because I like to begin talking about them there. So when we talk about intermolecular forces here, they start to come together a little bit more for you. If you didn't recognize already, this unit 3, it's kind of like a weird combination of a whole bunch of different topics, and it's worth quite a big portion of the of your AP exam grade. So this unit might go by relatively quickly because there's a lot of labs toward the end. There's not a lot of notes, I should say. We have to actually do a lot of things in order to understand this content. So anyway, let's actually get into the content. So in Unit 2 was all about ionic bonds and covalent bonds and metallic bonds. Those are what we called intramolecular forces. So all of Unit 2 was just about intramolecular forces. And these are the forces that are inside or within a single molecule. And typically these are going to be, for example, your covalent bonds, your ionic bonds, and your metallic bonds. Oops, forgot an S there. So everything that we've talked about in Unit 2 are your intra, because remember, that's what the prefix intra means. It's inside or it's within. They're what's holding the atoms together within a single molecule. Whereas our intermolecular forces are a little bit different. And this particular unit focuses on intermolecular forces. And the prefix inter means between. And in this case, it's the force of attraction between entire molecules. So that brings us to what are the 5 types of intermolecular forces between entire molecules. So there are 5 of them that we are going to talk about. And we talked about most of these in Chem 2, actually, but we're going to review them here because they are such a big part of the exam that I want to make sure you really understand these intermolecular forces. So the first one that I'd like to talk about is a London dispersion intermolecular force of attraction. And your London dispersion intermolecular forces are temporary, instantaneous, which means they happen in an instant, and very weak dipoles as a result of asymmetrical distribution of electrons around the nucleus. So this occurs within all atoms or molecules. So notice I did say the word atoms there. So a lot of times you'll see me draw pictures of atoms, and those pictures look a little something like this. You have your nucleus in the center, and you have your electron clouds, right? And they have these little shells that surround them. And typically we draw your electrons all in the shells. Now, I'm not being entirely accurate here, but I'm just trying to show you something that you might see. Now, for the most part, atoms will look like this, and your nucleus is going to be in the center, and all of your electrons are going to be distributed symmetrically around that nucleus. However, sometimes you might have your nucleus in the center, and you might have your 3 shells. But there could be a very brief moment in time where all of your electrons exist on one side of the atom or molecule. When this happens, we create a polar atom or molecule, right? Even atoms. This works with all of the noble gases as well. We could create a polar noble gas for just a split second. And that's because by chance, all of your electrons happen to be present on this side of the nucleus. Therefore, this side of the atom will have a partial negative charge, whereas this side of the atom has a partial positive charge. And therefore, we create this polar species for a very brief moment in time. And that can attract other nearby atoms or molecules. So London dispersion, intermolecular forces account for the trend in boiling point with the noble gases. So bring back those trends again, right? So, and the reason why I bring this particular trend up is because it really is such a beautiful trend of how London dispersion, intermolecular forces are so significant. So we have all of our noble gases here going down that last group. So I have helium, neon, argon, krypton, and xenon. And you'll see in this table down here, I also listed their boiling point in Kelvin. So helium has a boiling point of about 4.2 Kelvin. Neon is 27 Kelvin. Argon is 87 Kelvin. Notice it's increasing, 121 Kelvin. And then 166 Kelvin. Xenon has the highest boiling point, whereas helium has the lowest boiling point. Why would that be, right? The reason why something would have a very low boiling point is because its particles aren't attracted to one another. So we'll say particles aren't attracted. And if the particles aren't attracted, they are able to be farther apart from one another. Therefore, they vaporize much more easily. So because those particles aren't attracted as much, they vaporize very easily. Therefore, we have a very low boiling point. Because those helium atoms only have 2 electrons, if both of these 2 electrons happen to be on the same side of the molecule, this is only going to create a very small polar atom because 2 electrons isn't that much, right? This would only be like, it's just got 2 electrons there, 2 and a partially charged nucleus there with only 2 protons. So in this case, not really that strong of an intermolecular force. As I increase to neon, so neon has 10 electrons and 10 protons in its nucleus. So if all 10 of these electrons happen to be on the same side of this neon atom, we're going to create a little bit of a stronger partial negative charge because the more electrons means the stronger the charge. And therefore, this can more strongly attract other nearby neon atoms. This side of the molecule would be partially positive. So this has got 2 electrons. Neon's got 10 electrons. Argon has 18. Same thing, if all 18 of these electrons happen to be on this side of this atom, we create a little bit stronger than neon polar atom for just a split second in time. Granted, this only happens for an instant, hence that word instantaneous and temporary. As soon as this happens, it doesn't happen anymore. Krypton's got 36 electrons and xenon has 54. So because xenon has so many electrons that are surrounding that nucleus, it is able to more strongly attract one another. And because it more strongly attracts one another, of the noble gases, xenon would have the highest boiling point. And actually, there's one missing on there. Radon would be next. So radon would be over here. And radon has, I don't have a periodic table close by, but it definitely has more. I think it's like 80-something electrons. We would expect that radon would have an even higher boiling point because those London dispersion forces are even stronger. The more electrons means the stronger London dispersion forces. This is not just true for noble gases, but we can also use this to explain why are certain hydrocarbons, why do they have higher melting points than others? So for example, Here's just a whole bunch of different hydrocarbons that are listed. So hydro, of course, kind of sounds like hydrogen. And then I have carbon, which means it has carbon in it. So a whole bunch of different hydrocarbons. Starting off pretty small here. So methane, a small molecule, has a total of, let's see, 6 electrons plus another 4. We have 10 electrons here. Okay, methane's got 10 electrons total. And as I progress up, so of course, as I'm adding more carbons and hydrogens, my number of electrons increases. So I'll say most electrons there. And I have the least electrons there. Room temperature, that's what RT stands for. Room temperature is about 25 degrees Celsius, which is about 298 Kelvin, okay? Because methane, and oh, I should also say all of these are nonpolar. All nonpolar. And we could tell because there's no very electronegative element in there. I don't have any nitrogen. I have no oxygen. I have no fluorine. None of that stuff. So all nonpolar molecules. So if I consider methane, methane has 10 electrons. If those 10 electrons are on the same side of the atom or molecule, that's not going to create something as strong as paraffin, which has 30 carbons. So 30 times 6 carbons gives us 180, right? Plus another 62. We got over 200 electrons we have to account for in every single paraffin molecule. If all 200 of those electrons are on the same side of the molecule, that's going to attract other nearby molecules much more strongly. And because they attract those nearby atoms so much more strongly, paraffin is a solid at room temperature. That's why I like to make candles, because it's a great application of this. So granted, although paraffin does have the highest melting point in this case, it doesn't have a high melting point overall. And that's because these London dispersion forces, they're strong, but they're not that strong. We're able to account for trends as they increase with the number of electrons. So methane and ethane don't have that many electrons. These are gases at room temperature. Methane molecules and ethane molecules do not attract one another as strongly as propane and butane. So butane you can find in lighters, and propane you can actually find like when you fill up your grill or something like that. They're propane tanks. Propane is a gas, but it can be a liquid as well, and that's because its boiling point is right around where we're at. So if you consider butane, if you remember back to the molar mass of butane lab from Chem 2, butane is a liquid in the lighter, but once you pull that trigger, it's actually a gas. So it's an easily liquefied gas. And that's because butane particles attract one another more so. It could exist in the liquid state more readily. Gasoline and kerosene, we know those to be liquids, right? And liquids will attract one another. So we'll say more strongly attracted than gases. Okay, which is what keeps them in the liquid phase. If we consider a liquid, those particles are pretty close to one another, sitting at the bottom of the beaker. Gases, on the other hand, are very far apart. So these are far apart because they're not attracted to one another. Liquids are attracted to one another more so they like to be next to one another. Something like paraffin, I could draw these beakers a little bit bigger, you could see, but if I have a little paraffin flake in there, all of these particles are super duper duper close. Okay, they retain their shape, and that's because the particles like each other so much. Because they have these London dispersion forces, they're not going to let go of one another. So paraffin has the strongest, I'm writing a lot on this page here, strongest London dispersion forces, whereas methane has the weakest London dispersion forces. And we can use this trend with just about anything, as long as we're talking about similar atoms or molecules. So in this example, we looked at the noble gases. For this one here, we looked at some hydrocarbons. As long as we're comparing similar atoms or molecules, this is a great trend. So as molecular size increases, the number of electrons increases, which makes the London dispersion forces stronger. And really what it comes down to is this number of electrons, right? More electrons equals stronger London dispersion forces. And what do these stronger London dispersion forces lead to? Well, as we saw already, these do lead to higher melting points and boiling points. But these also lead to a lower vapor pressure. So let's talk about what vapor pressure is here for a second. We talked about this a little bit in Chem 2, but the vapor pressure is the pressure, I'm going to try to write this as best as I can, of the vapor particles above a liquid in a closed container. So here I have two examples, right? And both of these are in two containers. We have to remember that these are closed, so they're sealed right there. Sealed up, they got a cap on top. Let's take a look at both of the liquids in these containers. Here I have some substance, right? Here's its liquid. Here it is in the liquid state of matter. Here's its vapor. In this case, I have 3 vapor particles. So there's 3 vapor particles. Whereas in this one, it looks like I have a lot more. So let's count just to double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 particles total. The one on the left, 3 of them are vapor. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, make sure I count it right. 7, 8, 9, 10, 11, 12, 13, 14, 15. So in this case, I have 9 vapor particles. So which one of these substances has the lower force of attraction between one another? Well, it has to be this one here on the right. These red particles do not attract one another as strongly because they are much farther apart. They're able to separate from one another. Therefore, they're not attracted to each other. So your liquid particles are not as attracted to one another. Not as attracted, which leads to more particles exist as a gas. Because gases, as we know, tend to be very far apart relative to their size. In this case, because the particles like to be near one another, because they are very attracted, these are more attracted to one another, they tend to stay in the liquid phase. They want to be close to one another, okay, because they attract one another. Think about it. If you're attracted to somebody, you want to be near them, right? Same thing goes for substances as well. In the liquid phase, they're much closer together. So if they're more attracted to one another, they want to be closer. Here, we see that this substance is more in the liquid phase. Not as many gas particles that exist in this closed container. So we say that the vapor pressure is very low, okay? Not a lot of this substance will vaporize at room temperature. The pressure that this vapor is exerting on the walls of the container is very low, as opposed to this one right here. If I have more particles that are in this container that are hitting the walls, This has a much higher vapor pressure. If there's more vapor above the liquid, those vapor particles are going to hit the wall of the container, which exerts a pressure. So one of these, the one on the left, has the lower vapor pressure, whereas the one on the right has the higher vapor pressure. And we have to remember this relates to how volatile it is well. So volatile is its ability to vaporize. A lot of people think that volatile means it's bad for you. Volatile just means how easily it is to vaporize. If these liquid particles are very attracted to one another, this is not going to be a very volatile substance. If the particles stick together in the liquid phase, it's not going to vaporize very easily. So in this case, your volatility is very low, whereas if you have a sample of something that does vaporize very easily, we say that it's very volatile. Great example of each of these. Maybe I have oil for this one here on the left. Oil has a very low vapor pressure because oil doesn't vaporize as easily. We're not going to have very many of those oil particles evaporate. So its vapor pressure in a closed container is very low, and it's also not very volatile. Something that is very volatile would be gasoline, relative to oil, that is. If I have gasoline in a closed container, that gasoline is going to start to evaporate in the container. What does that do? The more gas particles that evaporate, the more pressure is going to exist in that container. You're going to have more particles that hit the walls of that container. It's more volatile, we say as well. There's a lot of stuff happening in here. So of course, if you have any questions, please let me know. But this is the whole basics behind London dispersion forces. London dispersion forces occur within all atoms or molecules, but it's a great example of when we can use trends to describe why, in particular, nonpolar atoms or molecules, or why with the noble gases do we see these trends. So we're going to talk more about this as we progress through these intermolecular forces. Let's also look at dipole-dipole in this video. So whereas our London dispersion forces occur between all atoms or molecules, go back to black here, we also have dipole-dipole intermolecular forces of attraction. So rather than have you write down a definition, I kind of started to do that for you here. London dispersion forces are instantaneous and temporary. So like I said, as fast as they happen, they're going to not happen anymore. Whereas your dipole-dipole intermolecular forces of attraction are permanent. That's because this occurs between polar molecules. Because polar molecules always have a dipole, they will always attract other nearby atoms or molecules, right? Whereas London dispersion forces, they kind of go back and forth. They start to attract, but then they can go back and become nonpolar again. They're instantaneous dipoles, and they're temporary dipoles. Dipole-dipole are a little bit stronger because they're permanent, okay? And molecules with dipoles are more strongly attracted to one another than those without dipoles. What we have to remember here, though, is this is only true when we deal with a similar number of electrons. Similar number of electrons in species. So something that has a dipole would be water, whereas we already said paraffin does not have a dipole, it's nonpolar. Based on that, we would say, all right, well, why is water a liquid and paraffin is a solid, right? Even though water has those dipoles. After a while, once you start to add those electrons, those London dispersion forces start to become really significant, which we'll do in some examples here as we progress through a little bit more. So Let's go ahead and look at each of these. So which of the following molecules will experience dipole-dipole intermolecular forces? So for the one that does experience dipole-dipole, show the force of attraction between two molecules. Which one of these has a dipole moment? Which one of these is polar? It's going to have to be this one right here. In this case, my charge is not canceled out. Your oxygen has your partial negative charge, whereas carbon has your partial positive charge. So carbon dioxide, we have that net dipole moment of 0. Those dipoles cancel out. So carbon dioxide, because it's nonpolar, would only experience those London dispersion intermolecular forces of attraction because it could have an asymmetrical distribution of electrons. Carbon monoxide can have that too, but because it has a permanent dipole, this could attract other nearby carbon monoxide molecules. And the partially negative end of one carbon monoxide molecule can attract the partially positive end of another carbon monoxide molecule. That is our dipole-dipole intermolecular force. Dipole-dipole. I usually abbreviate them as IMA, intermolecular force of attraction. Notice that these are drawn with dotted arrows. That's because these are much weaker than your intramolecular bonds, your covalent bonds, or ionic bonds, and your metallic bonds. This is why carbon monoxide is so bad for us to breathe in, because carbon monoxide is polar, whereas diatomic oxygen is nonpolar. Carbon monoxide bonds more readily to the heme groups in your blood. So you have those iron porphyrin groups. That iron has an overall charge that's positive. It's either +2 or +3. That oxygen can bind to that iron much more readily because it has a negative charge. So basically, it kicks all the oxygen out, and therefore you're basically suffocating from the inside out. And it has to do with this fact that carbon monoxide is polar, whereas your diatomic oxygen is nonpolar. And it attracts to those iron groups. You have like this iron group here, and then you have these like little rings, if I'm remembering my biochemistry correct. But you have these rings here that are attached. And then this is what transfers the oxygen throughout your body. I always found that very interesting. Of the pairs listed below, determine which would have the higher boiling point and explain why. So let's get this view back a little bit better first. So sometimes with these, it might be good to draw Lewis dot structures. So I'm going to draw the Lewis dot structure for hydrogen sulfide. Nice little bent molecule there. And I have hydrochloric acid. There we go. In this case, in hydrochloric acid, I have only one bond. So if I were to draw my dipole moment here, chlorine is quite a bit more electronegative than hydrogen. So in this case, my pull would be going more towards chlorine. For hydrogen sulfide, sulfur is a bit more electronegative than hydrogen, but I have two bonds to consider. I have a bond going up, but I also have a bond going across this way. And this is going to help us to determine which one of these is actually a little bit more polar than the other one. So your correct answer here is hydrogen sulfide. And that's because this particular molecule is quite a bit more polar. And that's because it has two lone pairs that are attracted to it. Most of your electrons are going to exist on sulfur relative to chlorine here. So one way that you can decipher boiling points with atoms that have similar number of electrons. So sulfur has 16 electrons, plus another 2 gives me 18 electrons total. And this also has 18 electrons. I can't really compare this by means of London dispersion forces because they both have the same number of electrons. So I have to look at how polar are these. And in this case, our hydrogen sulfide is a little bit more polar because it has two areas of partial negative charge. This guy has only one area of partial negative charge, which means these are less attracted to one another. So in this case, it has to do with those areas of electrons here. How about we look at this next one? Well, I have hydrogen sulfide, so let's draw this out. Another bent. And selenium is actually in the same group as sulfur, so it's right below it. Selenium looks like this. In this case, both of these have the same exact shape. They have the same number of lone pairs. Both of these are relatively electronegative. The pull is going to be about the same. So which one of these would have the higher boiling point? And because these have very similar shapes, we can't really compare number of lone pairs and one's more polar than another. But in this case, we have to look at the size of the atoms. Who has more electrons? Sulfur has 16 electrons. So in this case, the whole entire molecule has 18, whereas selenium has 34 electrons. So total, it has 36. Because selenium has more electrons, this guy right here, this hydrogen selenide, would have a higher boiling point because those London dispersion forces are much stronger. So we have to consider not only those London dispersion forces, but so we not only have to consider how polar they are, but we'll really have to look at which one has the most number of electrons. Notice that we're not saying that these have a higher mass. We say that these have more electrons. Generally, the phrase that chemists use is that we say that selenium has a more polarizable electron cloud. That means that it has more electrons, so that electron cloud can become more polar. It has a more polarizable electron cloud. That's where I'm going to stop for this particular video. This tends to be a little bit of a heavy topic. I do have some Chem 2 videos you can look at if you want to review some of those, because I believe I go in a little bit more detail there. So you're more than welcome to watch them. But this is going to conclude our first video on intermolecular forces. So we talked about London dispersion, intermolecular forces, and we also talked about your dipole-dipole intermolecular forces. As always, if you have any questions, please let me know, and I'll see you in the next video on some more intermolecular forces. Bye.